This is Jack Jackson. We're going to continue our look at the Fundamental Theorem of Calculus. So if you've been watching the last couple of videos, we've gone through a discovery method of looking at the fundamental theorem using our calculators, and we've discovered what Newton and Leibniz discovered in the 17th century. So in about 1667, this discovery was the crowning achievement of at least 4,000 years of mathematical development, and it's still one of the biggest achievements in mathematics and in human thought really today. It's called the Fundamental Theorem of Calculus. So let me kind of state that formally here. So the Fundamental Theorem of Calculus says there are a couple parts to it here. The first part says, well, in both parts, we let f of t be a function that's continuous on an interval t going from a to x, a closed interval. Then if we take f of t and we integrate it with respect to t from t going from a to x, and then that'll give us a function of x. If we then turn around and take the derivative of that function with respect to x, we'll be right back at our original function f evaluated at x. This is the first thing that we did in our exploration about 2 videos back. And then in the next thing that we notice is that if we were So let's go back. The first one, we took an integral first, then a derivative. If we reverse that and do a derivative first and then an integral, we take some function f of t, we take its derivative with respect to t, integrate with respect to t from a to x. This gives us a function of x, which is f of x, our original function, evaluated at x, minus f evaluated at a. Or equivalently, another way to say this second part is to say it this way. If f is any antiderivative of a continuous function g on this interval, then the integral from a to b of g of x dx is f of b minus f of a. So what this tells us, one way we can find a definite integral is by finding an antiderivative f. So the derivative of f is g. Okay. F is an antiderivative of g. G is the derivative of f. Then we take that antiderivative evaluated at both endpoints and subtract. So let's see if we can prove this. So notice that this says that in some sense, differentiation and integration are basically inverse operations. They sort of cancel each other out. So the first part says that the integral from a to x of f of t dt is a function of x whose derivative is the original function f of x. Okay, a function with this property is called an antiderivative of the function f. And the second part of the theorem says if we can get our hands on an antiderivative of the integrand function, then we can use this to find an exact value of the definite integral by finding the amount of change in this antiderivative. In other words, evaluate the antiderivative at both limits of the integral and subtract. Of course, if we've shown this works for 1 or 2 examples up above, or even 3 or 4 examples, that's still not enough for a proof. So we need to show that this works for any function f of t. And so before beginning the proof, let's recall a couple of definitions. Remember, a continuous function is defined this way. A function f is continuous at x equals a if and only if the limit as x approaches a of f of x equals f of a. So the function must exist there, the limit must exist, and they must be the same. An alternative definition of a continuous function that would be the same thing, is equivalent to it, is the limit as delta x approaches 0 of f of x plus delta x is f of x. See if you can convince yourself that that is going to be equivalent to being continuous. Now we're going to provide a proof of the fundamental theorem of calculus. And I will say that this is going to be informal in a couple of places. There are a couple of places that this is not a completely true, rigorous proof, but it gives you the basic idea of the proof, and I think it'll be instructive to go through that. So again, there's the statement that I said above. So what we can do to start with is think of the integral with a variable upper limit x. We can think of it as a signed area function a of x. So a of x is this function a, the integral from a to x of f of t dt. Then the derivative of that is going to be a prime of x. So our result, that the derivative of this is this integral is f of x, In other words, we're trying to prove that the derivative of this area function is f of x, and I should say probably a signed area. Okay. So we recall the definition of the derivative that a prime is defined to be the limit as delta x approaches 0 of a of x plus delta x minus a of x divided by delta x. Take that limit as delta x goes to 0. So, at least as long as f of t is positive, a of x is the area under the graph between t equals a and t equals x. Let's look at an illustration here. So this purple area here is the integral from a, let's say a is over here at this end, x is here. I've made a function that's always positive, so it's just so we don't have to worry about the sign of the area. But that purple area is the integral. And if we move over some delta x, which is just this amount here, the width of this little yellow piece, then this area here, well, we'll get to what that area there is in a minute, and this is x plus delta x is here. Okay, and the graph of the curve. So a of x is the same as the purple shaded area. And if you integrate from a to x plus delta x, so that would be a of x plus delta x would be the purple area plus the yellow area. And that's going to be the integral, well, that's going to be a of x plus delta x, which is the integral from 0 up to, from a up to x plus delta x. And then the difference, a of x plus delta x minus a of x, is just going to be the yellow shaded area. So this yellow shaded area is a of x plus delta x minus a of x. Well, let's think back to the rectangles we drew when we evaluated Riemann sums. If we were to approximate the yellow area with the left Riemann sum with one rectangle, what would the area be? Well, the width would be delta x and its height would be f of x, so its area would be L, which is f of x times delta x. So, if we were to approximate the yellow area, which is a of x plus delta x minus a of x, with a right Riemann sum, what would it be? Well, it would be f of x plus delta x times delta x. Now, if it's a continuous function, if delta x is small enough, then we can consider it to be all increasing, decreasing, and constant on hopefully a small enough interval. So if we sort of divide it up into small enough intervals, let's think of this as being all decreasing or increasing. So one of the two things happens. The yellow area is going to be between the left and right. So either if it's increasing on that interval, the right will be, if it's decreasing on the interval, the right will be too small and the left will be too large. So it'll be right, then the yellow area, then the left. So we get this inequality. Now divide all three parts by delta x, and we get a of x plus delta x minus a of x over delta x, which is the difference quotient there, is going to be greater than f of x plus delta x and less than f of x. If the function is increasing on the interval, it'll be reversed, so the right will be too big and left will be too small. But either way, you get it sandwiched between the f of x and the f of x plus delta x, it being the difference quotient. So what happens if we let delta x approach 0? Well, the stuff in the middle approaches what? Well, it approaches the derivative, and the thing on and this one doesn't have any delta x, so it stays the same. And the one on the right here, or the left up here, approaches f of x. So since it's a continuous distribution, or continuous function, this limit here is f of x, the limit in the middle is a prime, and this limit is, well, its limit of constant is delta x goes to 0, so it's just f of x. So, by the squeeze theorem, okay, we get a prime is f of x, and that's what we were trying to prove. Now, for part 2, if f is any antiderivative of a continuous function g, then we're saying that f prime of x equals g of x. So, again, as in part 1, we let a of x be this definite integral here with a variable upper limit. So by part 1, we know that a prime is the derivative of that function, that integral, which turns out to be the original f prime. Okay. So the function a and the function f have the same derivative function. Well, we know that this means that they must be vertical shifts of each other. One way to think about that is if you've got the same x value and two different functions have the same derivative, that means their tangent lines are parallel to each other. And if you zoom in close to those 2 points, the graphs look pretty much the same shape. Well, if that happens everywhere on the graph, then the two graphs have to have the same shape, the only difference being one is a vertical shift of the other. And of course, if you add a constant, you take the derivative of both sides, the derivative of that constant is 0. So we get this. So it turns out that that's the only way to make two functions have the same derivative is for either their functions are the same or they're just a vertical shift of each other. It's adding a constant to the function. So if a of x was, well, let's do a of a. Well, that's the integral from a to a, and, well, that's going to end up being a 0. So anytime you integrate from one number to the same number, doesn't matter what you put over here, you're going to get 0 for that integral. In other words, no area if you don't have any width. Now, let's look at this. F of b minus f of a. Well, f of b is a of b plus c. F of a is a of a plus c. When you distribute the minus, we get this. Notice that the c's cancel out and you get a of b minus a of a. A of a is 0, and so that's a of b. Now what is a of b? It's the integral from a to b of g of t dt. Or in other words, doesn't matter what I call this letter, I could say it's the integral of a to b of g of x dx. So we've seen that remember f was any antiderivative we picked of g of x. So that proves the fundamental theorem. Okay, we'll summarize and interpret all these results here just a little bit more in our next video.